Okay, well, this is the first lesson of calculus. Now it's really not even our first lesson, it's before our first lesson. And this is really just kind of a simple warm up. Hopefully, it gets us back sort of thinking math and reminds us of a few things. We're going to talk about a few other things. We're going to learn something that's going to be a little bit helpful for the first unit, but is not going to be a big part of the entire course. But still, in a way, it's our first lesson. So here we go. Before we even get to the lesson for today, I thought we could talk about some other necessary skills, get you thinking about the kinds of things you're going to need to be able to do from previous courses, some of the most important skills that you have to bring to this course from previous courses. So one of them is going to be factoring. And I would imagine everybody in this course is going to be very confident and good with their factoring. We're going to step it up a little bit. In Unit 2, you're going to notice that we really do take it up a notch. So, you want to be an expert at factoring. Obviously, we're going to be doing factoring of, quadratics and cubics and other things like that. But we're going to do some different kinds of factoring, some common factoring of some different things. So just factoring in general is something that's going to happen quite a bit. There's a fair bit of sketching in this course, so we are going to revisit sketching rational functions. So if you remember that from MHF, those are the big fancy curves that we do, right, that take a long time. And we are going to add some more detail to them so they get even bigger in calculus. So the basics of finding end behaviors and intercepts and that kind of thing is something that you want to do. And you can go back and reflect on how successful you were with these skills in the past in MHF and that kind of thing, and start thinking about those things again and remembering the details. We are going to we're going to graph some trig functions. Our trig functions are going to be quite different from the ones that you did in MHF. They're not going to involve transformations per se. They're going to be almost more like sketching rational functions. But all of the skills required come from the trig unit, so solving trig equations, all that kind of stuff. And then we are also going to sketch exponential and logarithmic functions, which exponential you should have done. Logarithmic, we looked at the graphs in MHF. We didn't really do a lot of sketching of them, but that is something that we're going to explore more in this course. Your algebra skills are going to have to be really good. This is the hard part. Calculus, they say, everybody says the ideas in calculus are quite simple, quite straightforward, quite easy. It's a simple concept, what we're going to look at for calculus. It's the algebra that is very, very difficult. Okay, it's finicky. It just takes a lot of care to do it properly. So and I'm not talking about your grade 9 algebra skills like adding 3x and 4x. That's the base of it, but it's going to get a lot more complicated, obviously, in this course. Finally, equation of a line. So this is something that we're going to be doing throughout the course, even into the vectors portion, although it's different certainly when we get to vectors, but it's related to the equations of lines that we already know. So this goes back to grade 9, point, slope, formula, and if you don't know that, that's fine. A lot of the stuff we're going to be revisiting and reviewing as we need it, but that is something that you're going to have to do. And the reason why I sort of was thinking about bringing these up and talking about these in the opening to this lesson is I think sometimes students take these for granted because they are skills from the past and they don't they don't quite get them. They don't spend the time to really review them, and then when it comes to the test, they realize they don't actually know how to do it because it's a grade 9 skill, and I learned it in grade 9. Yeah, but you might not have done it in a while, right? So this is something just to pay attention to, and it will probably be a simple thing. You just need to make sure that you can do it, and you can do it, hopefully easily, efficiently, that kind of thing. Okay, and then finally, work ethic. And I mean, this is something that teachers always say, but it really is true in this course. I have taught many very, very bright students who have done well in mathematics courses throughout their life. and but they don't really have that work ethic, and they get to calculus and they finally meet their match. Calculus is a different beast. Like I said, the algebra in it is very thick, and if you're not willing to take the time to practice, you're probably going to find that you're actually not that good at it. Like I said, it's simple, and this is deceiving. It looks simple, and a lot of what we do is just using a formula. So we're going to have a formula for how to do the things we're going to do. You say, oh, it's just a formula, so I just use a formula. But it's not that easy. This is the point, is yes, it's a formula, but using the formula and then cleaning things up is the algebra part, and it really does take practice, just like factoring. Factoring is a simple concept, whether you're talking about simple trinomials, complex trinomials, or whatever. It's a simple concept, but you have to practice to get good at it. So this is true of all of what we're going to do in the calculus portion of this course as well. And vectors is a little bit different, but that's not for a while, so we won't worry about that yet. But you really do need to take the time to practice and make sure that you are able to solve these problems, to accurately do the algebra, clean things up, not just understand the concepts. Okay, so those are some things to think about as we start the course. Some of them aren't going to happen for a little while, but these are sort of the main skills that came to my mind when I thought about what we're taking from the previous several years moving into this course, what we want to be good at, what we're going to need. All that being said, we are going to get into the point of this actual lesson, which is piecewise functions. That's the title of the lesson, piecewise functions. What is a piecewise function? So, piecewise function. Now, this comes down to, what is math really all about? What's the point of math? Why do we have math? And that's a big question, and we're not going to get too deep into it, obviously, but the point of math is we can use it to model our world. So we can come up with a mathematical model of something that happens in the real world, and an easy, obvious example of this is, physics. In a physics class, physics uses a lot of math. So does chemistry, all science, that sort of thing. And then we use that model to make predictions, okay, to predict what's going to happen, and then we make choices based on that prediction, or, whatever it is, whatever the situation happens to be. So that's really the point of math, is we use it to model the world around us. And so in grade 10, you learn about quadratics, and a common question is, a ball is tossed in the air and it follows a quadratic path. But here's the thing. In the real world, in math class, that's great. And when all the numbers are friendly and everything works really nice and it reaches its maximum at exactly 2 seconds, right? Like, everything works out nicely. But in the real world, nothing is that nice. The numbers are never friendly. They're never integers. And it just doesn't work that way, okay? And the reality of it is that in the real world, the things we model are not going to follow one relation. So sure, so I'm going to sketch a few examples of this, and you don't have to sketch this, you can just watch. So I'm going to put some axes here. Okay, so back to that same example of a ball being tossed in the air. So a ball gets tossed in the air, follows a quadratic path until, that wasn't a very good quadratic path, but that's okay, until it hits the ground. Well, what happens now? And in grade 10, we just ignore that. We're not worried about what happens from here on in. But what happens in the real world is the ball bounces. Well, what do you think that relation is for that bounce? Well, it's actually going to be quadratic again, isn't it? Because it's still just a ball being affected by gravity. And then it's going to bounce again, and then again, and then again, and again, again, and again. And it's going to trail off. And eventually, I suppose, it'll stop bouncing and it will roll. And that would be a linear function, right? That would be a constant function, actually, where it's just rolling straight along the ground. And then eventually it would stop. And so each one of these bounces would have a separate equation, right? So if we wanted to model the path of a ball beyond its first trajectory, after it starts bouncing, then we would need other equations. They would all be quadratic for the most part until the very end, I suppose. But, we would need more than one quadratic equation. I don't know why this is the case, but for some reason, profits are often modeled with quadratic relations. At least that's true in math class. We often use profits when we do quadratics. But again, they're only going to follow a quadratic path for a certain amount of time. So here's another example. You've got your profits are coming up. And so in grade 10, we say, well, and then they maximize, and then I suppose they go down. And that's the part that I don't really understand. Why do they go down? I don't understand why. I mean, there are explanations, and I usually, when I teach this, it comes up in several courses. We do give explanations for why, like you have overhead and that kind of stuff, but it's not really realistic for the real world. So I would actually imagine that they follow a quadratic path until they get to sort of the maximum there, but then they probably don't actually maximize. You can still increase your profits, and I'm going to guess maybe they follow some kind of logarithmic path from there. So, or like it looks a little bit like a square root, but logarithms go kind of like that. So you are still increasing your profits, but not as quickly as you did in the beginning. Or actually, maybe it's the opposite. Maybe you get to this point where your profits have matched all of your overhead, so all the research and development, and now every time you sell your product, whatever it is you're selling, you're actually just really making profit, and that would kind of be linear at that point, and maybe it would sort of rise that way, and you wouldn't have it trailing off. So it depends on the situation. It depends on the specifics, the product, whatever, right? But it does, I suppose, follow a quadratic path in the beginning at some point, but then it will eventually be modeled by some kind of other relation, whether it's logarithmic or linear or whatever it is, right? So that's another example. Another example that we often use is population growth is modeled by exponential relation. And that's the idea that if you have a population of rabbits, every rabbit will make 5 more rabbits, and then each of those 5 rabbits will make 5 more rabbits, and each of those 5 rabbits will make 5 more rabbits, and that is exponential growth. And so exponential growth looks like this, right? And grows really fast. But again, this is only to a point, because those rabbits have a limited food source. And they have predators as well. The more rabbits you get, the more predators are going to come into that situation. If you have a forest that is just full of rabbits, you're going to get a lot of predators attracted to that location, right? And so that's going to change the modeling of that population. So it's going to be exponential for a while, and then it's again going to trail off, and maybe it's going to eventually go down. I mean, who knows what it's going to do? Obviously, again, that depends on the specifics, but the point is that when you are modeling some specific thing in the real world, a population of rabbits, the height of a ball, whatever it is, profit for some product or of a company, it is going to fluctuate. It's going to go up and down. It's going to change over time. Different things are going to happen. So if you are only looking over the course of a few months, you might only have one function. But if you're extending that to more, to years or decades, then it is not going to follow a single relation. And that's what piecewise functions is all about. Okay, a piecewise function is a single function. Okay, look, it says a function. Okay, that is made up of more than one relation. Okay. The notation will include each relation as well as the domain on which that relation or that equation is to be used. So what is the domain where you're modeling with that relation? Okay. So there's two parts to each of it. And that's what we're looking at today. We're going to get a little bit of other practice. We're going to do a little bit of graphing, which is good because you want to be able to graph all the different kinds. You want to be able to identify and graph all the different kinds of relations that you've seen in the past. That's going to be really important. And we're going to do a little bit of function notation as well. But really what we're learning here is a new notation. Piecewise functions it's really just a way of writing out a single function that is made up of more than one relation. Okay, so it's notation. And if you've been in my class before, whenever we introduce new notations, so in MHF, it's when we do radians and when we do logarithms, I always have this discussion this is a new notation. Now, radians also has other sides to it, but with logarithms, it's really the notation that people are learning, and it takes time to learn. And what I always say is notation, usually at least, isn't hard. Okay, it's not difficult, but it's new, and it's something that you just have to get used to. And how do you get used to it? Well, by using it, by just getting familiar with it. Okay, so really that's what today is about, is just learning this new notation. And again, we're not going to use this notation much throughout the entire course. It's really just for the first unit, and as we introduce the concept of limits and we talk about that, this notation could be kind of useful. But really this is just a nice warm-up to get talking and get thinking and start doing a little bit of math and getting used to how our math classes run again, that kind of thing. Okay, so that's what we're looking at, and here is the notation. You can see that this is a single function, and the function's name is f. So f at x equals, and the function is made up of these two relations. Now, each of those could be a function in and of themselves. You could call them g and h or something like that. We don't in this case. You could. But in this case, we're not calling them functions. We're calling them relations because the function is the combination of the two of them. Again, this is just semantics in a way, and it's not going to be a big deal that we distinguish between these things because it's not going to come up. But technically speaking, that's the case. So how do we read this notation? Well, it looks like this function is made up of two relations, one of which is this. And what kind of a relation is that? And hopefully you realize it's linear. So this is one of the things that I was talking about, is we need to be able to recognize hopefully you knew that was a straight line, and maybe you didn't come up with the word linear, but it's a straight line, and we need to know how to graph it. We need to know its behavior, all that kind of thing. It's a polynomial, right? And what about the other one? So that's quadratic. It's also polynomial, degree 2, all that stuff. We know a lot about it, right? So we've got these two relations, one's linear, one's quadratic. And this function will look like this as long as the x value of the function is strictly less than -1. And it will look like this when the x value is greater than or equal to -1. So there's the boundary. That's the second part of the notation, the boundary where you are using one relation or another. Okay. And so here we go. So we're supposed to graph it and then determine each of the following. So we're going to look a little bit at function notation too, but that's going to be fairly trivial. It's not going to be all that interesting. But function notation is certainly something that is going to come up in this course. So it is something, it's another skill that we need to have and understand. Again, that's just a notation, but you need to know what that notation means. When you first learn function notation, it's actually very complicated. Some people struggle with it. They really don't get it. Maybe not this kind of a question where it's just f at -2, but if it's like f at g at x, that really can throw people off, right? Or maybe g at 2. And this is something that will come up in this course. So that is important that you understand that. But we'll get to that when we get there. Now, how are we going to graph this? So we'll graph each part separately. And we'll start with the top part because why not? And the top part is linear, so that's a straight line. How do we graph a straight line? So this is the kind of thing that, and I've talked about this in the past, and probably your other teachers, if you've never had me, if you've had different other teachers, they've talked about the same thing, is when it's something simple like this, you can't afford to spend a long time, if this is a test, thinking about how to do this. This is something you want to dive into. And this is when I say you need to be efficient in your work. There are certain things that you do not want to spend a lot of time thinking about. You just have to know how to do it, right? And those are the little things, the skills we've mastered from the past, like factoring and that sort of thing. So for this one, how do we graph a line? Slope and y-intercept. Okay, so this is like, don't write this down. I'm just going to scribble some stuff out. Y equals mx plus b. If I changed this to y equals mx plus b, it'd be y equals negative x plus 3. So my slope is negative 1. Whoops. And my y-intercept b is positive 3, right? So if I come over to the graph, I go up to 3. Slope of negative 1 would be up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Okay, something like that. Now, when we come back, we have to remember only when x is less than negative 1. So this line won't actually get to the y-axis. It will only get to where x is equal to negative 1, which is that point. So let me get rid of some of that. And I think I have to tilt this a little bit. Whoops, that might have been too much. Too much again. Hopefully that's about right. That looks pretty good. Use my ruler. And where were we? We were right there at negative 1 here. And I'm going up to the left, up 1 over 1, up 1 over 1. That way. I should have erased those dots. And what we're going to do, and again, this is a notational thing, is we're going to put an open circle at that point. Again, if I had continued this through, I would have gone through positive 3 because that was the y-intercept of that relation. But this function doesn't behave like this relation past negative 1. And why is it an open circle? It's important that I drew it as an open circle, not a closed circle. Okay, it shows that the point is not included. It's strictly less than. Okay, next, how do we graph quadratics? Well, quadratics we graph with transformations, and this is not written in transformation form. What is transformation form? It's y equals a, and we don't really usually use k when we're doing quadratics, and I'm not going to get into why that's the case, but we don't. Something like that. So if I were to rewrite this relation, it would look like that. So I've got a vertical shift up 2 and a reflection in the x-axis. And again, this is something that, and we're not going to draw a lot of parabolas to tell you the truth. It's going to be more straight lines, but and more working with equations of lines. But still, if it came up, this is something that you need to be able to do proficiently, which means accurately, and efficiently, which means quickly without a lot of effort. All right, so this is a graph that has a shift up 2. So look at that. Looks like my vertex, it didn't have any shift left or right. So my vertex is right there. And it has no stretch or compression. So, and I'm going down. So I'm going down to here and to here. And then when I go over 2, I square it and I go down 4. And over 3 and square it, I go down 9. So that's 4, 5, 6, 7, 8, 9, and so on. And again, this only takes this shape. This function only takes this shape when we get to negative 1. So I don't need to go down on the other side like that, right? And so let's graph this. Something like that. Now this one includes the point. So notice that I have a filled in point there. It looks like it was just the point that I drew when I was graphing, but I actually did that on purpose because it includes that point. And there you go. This is the graph. So I don't know what this would represent in the real life, but that's what the function would look like. And the pieces don't connect, and that's fine. There's certainly no rule that they have to. That's something that we're actually going to spend a whole day on, is talking about what happens when you've got these breaks in the graph like this. But for now, we're just sort of practicing graphing and getting used to this notation. So there is the visual representation of that function f. Determine each of the following, f at negative 2. So if we're just doing this from the graph, then all I do is go to negative 2 and find out where it is. But if I'm doing this algebraically, then what I have to do is I have to figure out, well, this x value, which domain does it fit into? And it's the top one. Therefore, I use that relation, right, that equation, to determine this. So it's going to be negative x plus 3. X is negative 2, so that's 2 plus 3, which is 5, which we saw from the graph. It matches up with what we did on the graph, but notice that we do have to make a decision based on the x value. What domain are we in? F at 0. Well, now I'm in the other one, right? 0 is greater than negative 1, so this is going to be 2 minus 0 squared, which is 2. Does that fit with our graph? Sure does. F at negative 1. Ooh, so this is obviously, I know this isn't actually a tricky question, but, you know, it's obviously not random. And again, we have to be careful that it is included in that domain. So this is the quadratic again. Negative 1 squared is 1. 2 minus 1 is 1. So that's 1. And again, that fits. All right. I think we have a couple more. We'll do these a bit quicker. For this one, I've got a linear and I've got a square root. And again, square root is one that we will do with transformations. Okay. And so here we go. We'll graph it first. 2 minus x. So this has a slope of negative 1 and a y-intercept of 2 when x is less than 3. So I can actually start at 2 because it's going to be less than 3. 3 is here. Okay. And strictly less than, and it's just a slope of 1 again. So this will probably work. I think if I go 43, it's going to be too much. Yeah. 44 is not quite perfect, but it'll be close enough. Okay, and again, it was not including the point at positive 3 here, so open circle. Okay, square root function. So square root function has a reflection in the x-axis, a shift to the right 3, and a shift down 1. So right 3, down 1, and it looks like I'm starting at this point, okay? And it's reflected, so from here, I go over 1, square root of 1 is 1. I go over 4, square root of 4 is 2. I go over 9, which goes off the graph. Square root of 9 is 3, so I don't want to get down to 3 before I get off the graph. Let's see if I can do this. Something like that, okay? And notice that they connect, and sometimes they do, sometimes they don't. Again, this is something we're going to talk about. It turns out that's actually kind of an important idea. Sometimes, for us right now, sometimes they do, sometimes they don't. If this was a population graph, then they would, right? Even if there was some, I guess if there was some cataclysmic drop in the population, like there was suddenly a big storm, a big tsunami or something that wiped out a bunch of the population, they would kind of suddenly cease to exist. But, you know, you could argue that that's just a quick drop, not an immediate drop. So anyway, generally speaking, we would think that all the different parts would connect. So in the real world, maybe this is what we would expect to look like, but not always, certainly not always. Okay, f at negative 2. So negative 2 is less than 3. I know I'm going through this quickly now, but I think hopefully we've sort of done the preamble, and that, like I said, now we're just starting to get warmed up and getting used to doing math again. So 2 minus negative 2, which is 4. Does that match the graph? At negative 2, we're at 4. It sure does. Whoops. We'll do that. Now, this square root doesn't even exist at negative 2, right? Because square roots have a bound under which they're for the domain, right? But let's say it was a question that didn't. You know, so for example, up here in this one, we found negative 2 again, didn't we? Well, this quadratic certainly has a value at negative 2. But that would be wrong for the overall function. So it's not like, even if you can sub in and get an answer, 5 is the correct answer for this function, not -2, which is what it would be for that relation, right? So again, we're talking about the difference between a relation and a function that has its own domain. And then at 3, again, that's going to be this point that is included there. So we do negative square root of 3 minus 3 minus 1, which is 0, minus 1, which is -1. And that was the case. Okay, one more. If you want to pause and try this one yourself, I think that's a great idea. Pause the video and try it yourself. Go for it. And then you can unpause and watch and check your answer and make sure that it's right. Notice that this has 3 parts. There's no limit, obviously, to how many different parts, different relations you could have in an equation. Looks like we're linear, then we're quadratic, then we're linear. And again, the second part of this notation gives us the domain. In this case, it's only quadratic for a section of the graph. The rest of the graph is linear, but 2 different linears. Okay. And so let's go ahead and graph it. So when x is less than -3, we are x plus 3. So x plus 3 has a y-intercept of 3. So I'm going to go 44 again, but the other way, because this has a positive slope. So notice how I've set my ruler up to be at +3 there. But I'm going to go to -3 and actually start graphing it, right? And I'll wait to, like, this would be an open circle, but I'll wait. I won't do it right now. I'll do it after. So that one's done. Between -3 and +2, we look like a quadratic. This is a quadratic in transformation form. That's useful. It has a shift left 1 and down 4 and no stretch compression and no reflection. So left 1 and down 4 looks like my vertex should be there. From the vertex, I go over 1, square it, that's up 1. Over 2, square it, that's up 4. And look at that. It connects with the first part. Over 1, up 1. Over 2, up 4. Over 3. And over 3 takes me to +2, which is the last boundary line, and it's excluding that point. So over 3 and square it up 9, so that's 4, and then 9 more is 5. So I'm going to that point. Oops, that wasn't very good. Try that again. Something like that. And then the last one is 2x minus 1, so this has a slope of 2 and a y-intercept of -1. So from -1, I'm going up 1, over 1, up 1, up 2, over 1, up 2. Wait a minute. Starting at -1, I go over 1, up 2, over 1, up 2, and this is where this graph starts. So, and it's including -2. That's kind of big. Let me do that again. Over 1, up 2, over 1, up 2, over 1, up 2. There we go. Hey, that looks good. So there you go. So this is, again, a bit of a different graph, and you can start to see that we could have lots of different graphs that take lots of different shapes. And this one has one part that is connected, one part that is not connected. And oh well, so what? That doesn't really mean anything for us because these are just math questions for a math class, not real world questions. But again, that is relevant. And then finally, f at -3. Well, we include -3 in the quadratic, so this is going to be the quadratic. So that's -3 plus 1 squared minus 4, which is -2 squared is 4. 4 minus 4 is 0. At -3, we were indeed at 0. F at 0 is again in the quadratic. So this looks like 1 squared, which is 1, minus 4, which is -3. At 0, we are at -3. And f at 2 is in this one, right? Because again, that's where it switches from one to the other. Four minus 1 is 3. And it is indeed 3, not 5. Is the correct answer for this one. There's no no room for arguing here, right? It's not like it could be one or the other. It is definitely just 3. So that is piecewise functions. I believe that is the last example. Like I say, pretty straightforward, fairly simple, just a simple warm-up for this course. This is going to be very helpful, in particular in the very first day when we start looking at the definition of a limit. We don't necessarily need to have the equations, so we're not going to do a lot of this kind of notation, but it's going to come up a little bit. And it is, I think, very good review to do this kind of graphing, and again, just get used to these kinds of little things. So hopefully that was straightforward for you as well, and you'll be ready to roll when we start our first real lesson of the course, where we're learning new stuff and start to scratch the surface of what we need in order to start exploring calculus.